Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, I will talk about the first three topics govern or consist in electrostatic chapter, which is Maxwell equation, charge, and the current density. Alright, let's look on the Maxwell equation first. So generally, the Maxwell equation is the fundamental equation that represent or tell us about what is happening in an electromagnetic field. So there is four equations that govern under this Maxwell equation. So the first equation which is del dot vector of D is equal to rho V. So this is the first equation. So the second equation is del cross with vector of E equal to minus del vector of B divided by del T. The third equation is del cross vector of B is equal to 0. And the last equation is del cross with a vector of H is equal to vector of J plus delta vector of D divided by delta T. So all these equation is consist of all component that having in electromagnetic field, as we have been learned before. So electromagnetic field consists of electric field and as well as magnetic field. So the first two equation is the equation that associate with electric field, whereas we have another expression that explain relationship between the vector of D and E, whereas the vector of D is equal to epsilon multiplied by the vector of H. So the last two equation of Maxwell equation, so this equation is represent or associate with a magnetic field, whereas in this equation, so we have another expression that represent relationship between the vector of B and the vector of H, whereas the vector of B is equal to mu vector of H. So what is means by each symbol that having in this equation? Alright, so first let's look on the electric field component first, which is represented by the first two equation of the Maxwell equation. So whereas we have the vector of D, so the vector of D is represent electric flux density. So the unit for this vector is coulomb per meter squared. So along this topic, you might find another component which is having the same unit, what we call it as a surface charge density. So in this particular case, so you need to be very careful to distinguish whether that particular value given to you is represent either the vector of D or electric flux density or represent the surface charge density. So the second component, which is rho V, which is one of the component consists in electric field, is we call it as rho V is equal to volume charge density, and the unit for rho V is coulomb per meter cubic. So the third component is the vector of E. So the vector of E is represent electric field intensity, and the unit for this particular vector is volt per meter. So even though, so we have another component which is vector of J. Even though this vector of J consists in another second part of the Maxwell equation, which is the equation that represent magnetic that associate with a magnetic field, but in this particular case, this vector is belong to component that having inside the electric field, whereas the vector of J is equal to current density, and the unit for this vector is ampere per meter square. So let's look on the definition of the component that consists in the magnetic field. So we have the vector of B here, So this vector is represent magnetic flux density. So the unit for this particular vector is Tesla, and the vector of H is represent magnetic field intensity, and the unit for this particular vector is ampere per meter. By looking into this expression that relates or explain the relationship between D and vector H, and as well as the vector B and the vector H, so we have another constant, we call it as a epsilon and mu. So this parameter is a parameter that relate or dedicated in a material component. So whereas the epsilon is represent electric permittivity, so the unit for this particular constant is farad per meter, and the mu is represent permeability, and the unit for this particular component or for this particular parameter is Henry per meter. So these two parameter is depending on the material, and each material having their own value. Alright, so since in the first chapter, so we are considering a static characteristic. So in static characteristic, so we might have delta over delta t will be equal to 0. So therefore, if we refer back to our Maxwell equation, so we will have this part and this part of equation will become 0. By considering this factor, so we will have another set of Maxwell equation that will be useful in analyzing static field. So we have del dot vector of D is equal to rho v. So the first equation will be maintained as the original form as we have been looked just now. However, in the second equation will be changed in terms of its form, whereas the del cross with the vector of E is equal to 0. So in this case, we are having delta B divided by delta T is equal to 0. So the first two equation is the equation that will be used whenever we are trying to analyze the field parameter in an electrostatic condition. Another two expression of Maxwell equation will be del cross with vector of B is equal to 0, and del cross with vector of H is equal to vector of J. Because in this particular case, so we will have the delta vector D divided by delta T is equal to 0, with the fact of we are considering our field in a static condition. So by referring into this static Maxwell equation, so we will find out that the electric field can be separate from the magnetic field. Compared to whatever we have here, so even though the first two equation is represent the equation that govern in the electric field, so however, for example, on the second equation, so we still have the component of magnetic field exists in this particular equation. Similar to the second pair of the Maxwell equation, especially for the fourth equation, so even though this equation is the equation that govern in a magnetic field analysis, so however in the fourth equation, so we still have the parameter or the component that exists in the electric field, even though this part of equation is represent the analysis that we need to, the equation that we need to use when we analyze a magnetic field. So however, even though we can separate the electric field from the magnetic field, so based on the first two equation that govern in the Maxwell equation, so however, based on the second set of Maxwell equation, which is the equation that associate in the magnetostatic analysis, so in this case, so we will have the magnetic field is only exists due to the existence of the current by referring to the fourth equation of Maxwell equation. Alright, so let's move to the second topic, which is charge. So the electric field source is come from a charge, and the charge can be represented by using its absolute value, which is particle charge, and the unit of it is a coulomb. And the charge also can be represented by using its density value. So the density value can be divided into three types. So the first is line charge density. So the unit of it is coulomb per meter. The second type is surface charge density. So the unit of it is coulomb per meter squared. And the last one is the volume charge density, and the unit of it is coulomb per meter cubic. When we having the charge is represented by its absolute number, so we consider of a single particle charge. So the single particle charge is the simplest form of a charge. So the value of it, either we have a positive or negative Q, and the unit of it is a coulomb. In the density value, so let's say we have a shape of cylindrical shape, and the charge is evenly distributed inside this shape. So we have area of this cylinder is equal to delta S, and the height of this cylinder is equal to delta L, and the volume for this shape is equal to length multiplied by its surface. So first, let's consider if we have the delta S or the surface is near to 0 meter squared. So in this case, so we have the shape of this cylinder is become this shape, whereas we will have our length is more significant to the surface on this side. So if we have this case, so the charge in this particular case will be represented by its line charge density, or we call it as a rho L, and the unit of it is equal to coulomb per meter. So in order to find the total charge exists in this particular line, so we just integrate the rho L value by using line integration against dl, and the dl will be represent or depending on the axis that we are used. On the second case, with the same shape, so in this case, so we are assume that if we have the delta L, or the length of this particular cylinder is near to 0 meter. So in this particular case, so the shape of this cylinder will become this shape, whereas we will have our surface is more significant compared to the thickness of this cylinder. In this particular case, our charge will be represented by its surface charge density, or we represent it by using rho S, and the unit of it is equal to coulomb per meter squared. So in order to find the total charge exists in this particular surface, so we just need to integrate to perform a surface integration of rho S dot with ds. So however, if we have the delta L and the delta S is not equal to 0, so we will have the original surface or the original shape of whatever we have just now. In this particular case, the charge will be represented by its volume charge density, or we represent it by using rho v, and the unit for this particular charge is equal to coulomb per meter cubic. Therefore, in order to find the total charge have in this particular shape, so we just performing a volume integration of rho v dot with dv. Alright, so in order to understand this topic better, so let's look on some example. So we need to find the total charge Q if the charge is represented by, first is by using its line charge density. The equation is equal to 2z, and the length of this line is from 0 until 10 centimeter. The second, the charge is represented by its surface charge density. So the equation of this rho s is equal to 2 multiplied by 10 power of 2 r, and this is the limit of the r, the radius of the cylinder, and as well as the angle. So last one, so in this particular case, its charge is represented by its volume, the charge density, and in this particular case, rho v is equal to 3r multiplied by 10 power of minus 4. So in this particular case, so we know that this charge is in a spherical shape, and this is the limit for the spherical shape. Alright, so first let's solve the first equation first. So whereas we have Q is equal to line integration rho L dot dl. So since in this particular question, the charge is given in the line charge density, so we just put whatever parameter that has been given. So the rho L is given by 2z. So in this particular case, since our charge is reside on the z-axis, so dl will be equal to dz, and the limit for this integration is given by this limit is from 0 until 10 cm. So therefore we will have z is equal to 0 until 0.1. So by solving this equation, then we will have the total charge in this particular case is equal to 10 power of minus 2 coulomb. On the second question, since the question gives us the representation or the value of Q, or the value of charge in the surface charge density rho s, so in this case we need to perform surface integration of rho s dot ds. So based on this limit, so we know that our ds is equal to r dr d phi, and the rho s is given by this equation, so given in this particular question just now, and the limit as well is based on whatever has been given in the question. So when you solve this expression, then we will have the answer for this particular question is equal to 11.31 millicoulomb. For the last question, so we need to find the total of charge, whereas the charge has been represented by its volume charge density rho v. So in order to solve it, we need to perform volume integration of rho v dot dv. So since in this particular case, so the shape of this charge density is in a spherical shape, so we can replace the dv into this equation, whereas the equation that represent the volume integration in a spherical coordinate system. By solving this equation, then we will have the total charge in this particular case is equal to 0.61 nanocoulomb. Alright, so now let's look the last topic in this video, which is the current density. Even though in a circuit analysis we are more concerned about the current value, so however in a field perspective, instead of the value of the current, so we are more interested in terms of its current density. So let's consider, so we have one conductor here. The conductor shape is in a cylindrical shape. So inside this conductor, the value of charge or the charge has been evenly distributed inside it, and the value of charge is represented by its volume charge density. So the charge is moved from one point to another with the speed of given is represented by this vector of u. If we extend a bit the conductor from this point to this point, So we will have, in this particular case, the length of a conductor has been extended with delta L here, and because of we didn't put any, or didn't, the area of this particular conductor is not changed, or is the same between the first part and the second part. So we will have the area of this conductor is equal to delta S. So by looking into this area, so in order to find the delta Q here, so we can have the delta Q is equal to rho V. So this is the volume charge density multiplied by the volume. So in this case, so the volume is referring to the second part of this conductor. Based on the second part of the conductor, so the volume of the conductor can be calculated by using delta L multiplied by delta S, which is the length multiplied by the surface area. So by replacing this expression into this expression, so we will have delta Q is equal to rho V, delta L, and delta S. At the same time, so we will have the electron is moved, or the charge is moved from one to another with the fixed velocity that represented by this vector of u. So therefore, the magnitude for this vector is equal to u is equal to delta L divided by delta t. So by rearrange this equation and then put inside this equation, then we will have the another equation that represents delta Q is equal to rho V delta S u multiplied by delta t. So let's consider the direction of the velocity and the area is not the same, or is not parallel. So that we will have the delta S here, or the delta surface here, is given in a vector form is equal to n cap multiplied by delta S, whereas this is the unit vector for the area. So by considering into this equation, then we will have the delta Q is represented by rho V, vector of delta S, vector of U, and as well as the delta T. As we have been known before, so we have delta I is equal to delta Q divided by delta T. So therefore, by considering these two equations, so we can have delta L is equal to rho V, vector of delta S multiplied by the vector of U. Then we will introduce another vector here. We call it as delta J, or the vector of J, and the vector of J is represented by this expression, whereas vector of J is equal to rho V multiplied by the vector of U, and the unit of this particular expression is equal to ampere per meter square. Then we will have delta I is equal to vector of J multiplied by vector of delta S. So in order to find the total current, so we need to integrate this expression. So therefore we will have I is equal to surface integration of vector of J dot the vector of surface. Basically, we have two types of current. So first is what we call it as a conduction current. So this conduction current is quite familiar with us, whereas during we are studying about circuit theory, so most of the time we will consider the current that flowing inside that particular electrical system is a conduction current. And this current is due to movement of the electron from one atom to another. So normally that particular condition is happen in a host material, so we call it as a conductor, and then that particular current is obey Ohm's law. So whereas in a circuit theory, so we have V is equal to I multiplied by R, which is the equation that represent our Ohm's law. So in this particular type of current, so the J or the current density, we call it as a conduction current density. So we have another type of current, what we call it as a convection current. So this current is due to actual motion or actual movement of a charge. So like what we have in lightning condition or lightning occurrence. So whether the charge is moved from the cloud to the cloud or the cloud to the Earth's surface. So this current basically is not obey Ohm's law, and the current density that happen in this type of current, we call it as a convection current density. Alright, so in order to understand this topic, so let's see one example. So let's say we need to find the total current if the vector of J is given by this equation and flowing through a surface of a spherical with the radius is equal to 5 meter. Alright, so in order to solve this problem, so we need to integrate this vector by using surface integration vector of J dot vector of ds. So in this case, because of we deal with the spherical coordinate system, so the vector of ds is represented by this equation. So r cap r squared sine theta d theta d phi. Then we put all the parameters that we know inside this equation. So we have this equation, and because of we not being supplied in terms of the limit of the theta and the phi, so that we need integrate it in a full scale of theta and phi. So the limit for delta is from 0 until pi, and the limit from phi is from 0 until 2 pi. By solving this integration, so you will find the total current in this particular case is equal to 314.2 ampere. Alright, so that's all for this time. So should you have any problem or any question, so please do not hesitate to ask or to submit your question in the ULEN. Alright, thank you, good luck and have a nice day.